Here we're trying to fit an appropriate polynomial to this data set. We're going to try to find the function that fits this data set, just the way we found the quadratic function that fit 3 data points for the flow data. We're going to find a polynomial that fits the 4 data points, or at least we're going to write the equations that we'd have to solve to find that polynomial. And we note that if we have exactly 2 points in our data set, of course we have 4 here, but if we had exactly 2, a linear fit would work. Obviously, if we have 2 points in a graph, there's a straight line through those 2 points. All we have to do is find the equation of that straight line. And as we saw early in the semester, a quadratic function will fit 3 points exactly. We can go on. A cubic function would fit 4 points. A 4th degree would fit 5. In general, a polynomial of degree n would fit n plus 1 data points exactly. We see that this data set contains 4 points. As a result, we're going to use a cubic polynomial to fit it. And just as we did with 3 points in a quadratic, we simply plug the coordinates of the points into the function model here, and we're going to get a linear equation. And since we got 4 points, we're going to get 4 equations with A, B, C, and D as the unknowns. And we see that right here. Okay, this is what we get. If we plug the point 2, 3, then x is going to be 2 and y is going to be 3. Next point is 5, 8, so x is 5, y is 8. Next point is 7, 6, x is 7, y is 6. Then 10, 12, and I haven't completed these. But we get these 4 equations, and this question again was to determine what the 4 equations were that would fit the given data set. Now we look at the graph of y equals quantity x minus 2 squared times x plus 4 times x squared plus 5x plus 8 near x equals 2. Now, near x equals 2, x minus 2 goes through some drastic changes. If we're just a little bit, if x is a little bigger than 2, this is going to be positive. If x is a little less than 2, this is going to be negative. So this thing changes its values fairly drastically near x equals 2. Whereas the rest of the function doesn't. The rest of the function is not all that sensitive to changes near x equals 2. Near x equals 2, then, x plus 4 is going to be 2 plus 4. X squared plus 5x plus 8 is going to be this, just substituting 2 in for x. And we see that y is going to be approximately equal to 132 times the quantity x minus 2 squared. Near x equals 2, this number, 132, doesn't change much. Near x equals 2, this thing changes its behavior a whole lot. And the whole expression changes its value a whole lot because of this, not because of this. As a result, near x equals 2, this function behaves like a quadratic function with a 0 at x equals 2, with a vertex at x equals 2. We can see that this is just a vertical stretch of the y equals x squared parabola by a factor of 132, pretty big stretch, and a horizontal shift by 2 units. And that the graph will therefore look something like this. The brown graph here is supposed to represent the parabola y equals 132 times the quantity x minus 2 squared, and this magenta graph is the actual polynomial. And it's supposed to represent the actual polynomial. I think that might be a fairly accurate representation, but you can check that out with derived. The polynomial might be displaced over to the right rather than to the left of the parabola. But the closer we get to x equals 2, the closer these graphs are going to be. Even if we magnify them, if we zoom in on this part of the graph, they're going to get much closer. They're going to be much more like the same graph. Because the rest of the polynomial, except x minus 2, gets much closer to 132. As closer we get to 2, the closer the rest of the polynomial gets to 132, so the closer these two graphs are going to be.